a WikiVidi Documentaries production. Don't forget to like and subscribe. Enjoy. Prime number. A prime number is a natural number greater than 1 that cannot be formed by multiplying two smaller natural numbers. A natural number greater than 1 that is not prime is called a composite number. For example, 5 is prime because the only ways of writing it as a product, or, involve 5 itself. However, 6 is composite because it is the product of two numbers that are both smaller than 6. Primes are central in number theory because of the fundamental theorem of arithmetic. Every natural number greater than 1 is either a prime itself or can be factorized as a product of primes that is unique up to their order. The property of being prime is called primality. A simple but slow method of checking the primality of a given number n, called trial division, tests whether n is a multiple of any integer between 2 and \sqrt. Faster algorithms include the Rabin primality test, which is fast but has a small chance of error, and the AKS primality test, which always produces the correct answer in polynomial time but is too slow to be practical. Particularly fast methods are available for numbers of special forms, such as Mersenne numbers. The largest known prime number has 23,249,425 decimal digits. There are infinitely many primes, as demonstrated by Euclid around 300 BC. No known simple formula separates prime numbers from composite numbers. However, the distribution of primes within the natural numbers in the large can be statistically modeled. The first result in that direction is the prime number theorem, proven at the end of the 19th century, which says that the probability of a randomly chosen number being prime is inversely proportional to its number of digits, that is, to its logarithm. Several historical questions regarding prime numbers are still unsolved. These include Goldbach's conjecture that every even integer greater than 2 can be expressed as the sum of two primes, and the twin prime conjecture that there are infinitely many pairs of primes having just one even number between them. Such questions spurred the development of various branches of number theory, focusing on analytic or algebraic aspects of numbers. Primes are used in several routines in information technology, such as public key cryptography, which relies on the difficulty of factoring large numbers into their prime factors. In abstract algebra, objects that behave in a generalized way like prime numbers include prime elements and prime ideals. Definition and examples. A natural number is called a prime number if it is greater than 1, and cannot be written as a product of two natural numbers that are both smaller than it. The numbers greater than 1 that are not prime are called composite numbers. In other words, n is prime if n items cannot be divided up into smaller equal size groups of more than one item, or if it is not possible to arrange n dots into a rectangular grid that is more than 1 dot wide and more than 1 dot high. For example, among the numbers 1 through 6, the numbers 2, 3, and 5 are the prime numbers, as there are no other numbers that divide them evenly. 1 is not prime, as it is specifically excluded in the definition, and are both composite. The divisors of a natural number n are the numbers that divide n evenly. Every natural number has both 1 and itself as a divisor. If it has any other divisor, it cannot be prime. This idea leads to a different, but equivalent definition of the primes. They are the numbers with exactly two positive divisors, 1 and the number itself. Yet another way to say the same thing is that a number n is prime if it is greater than 1 and if none of the numbers 2, 3, \dots, n1 divides n evenly. The first 25 prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, 97. No even number n greater than 2 is prime, because any such number can be expressed as the product 2 times n/2. Therefore, every prime number other than 2 is an odd number, and is called an odd prime. Similarly, when written in the usual decimal system, all prime numbers larger than 5 must end in 1, 3, 7, or 9. The numbers that end with other digits are all composite. Decimal numbers that end in 0, 2, 4, 6, or 8 are even. and decimal numbers that end in 0 or 5 are divisible by 5. The set of all primes is sometimes denoted by \math4 by \math. History. The Rhind mathematical papyrus, from around 1550 BC, has Egyptian fraction expansions of different forms for prime and composite numbers. However, the earliest surviving records of the explicit study of prime numbers come from ancient Greek mathematics. Euclid's Elements proves the infinitude of primes and the fundamental theorem of arithmetic, and shows how to construct a perfect number from a Mersenne prime. Another Greek invention, the sieve of Eratosthenes, is still used to construct lists of primes. Around 1000 AD, the Islamic mathematician Al-Hazin found Wilson's theorem, characterizing the prime numbers as the numbers in that evenly divide +1. Al-Hazin also conjectured that all even perfect numbers come from Euclid's construction using Mersenne primes, but was unable to prove it. Another Islamic mathematician, Ibn al-Bana al-Marakushi, observed that the sieve of Eratosthenes can be sped up by testing only the divisors up to the square root of the largest number to be tested. Fibonacci brought the innovations from Islamic mathematics back to Europe. His book Liber Rabbeci was the first to describe trial division for testing primality, again using divisors only up to the square root. In 1640 Pierre de Fermat stated Fermat's little theorem. Fermat also investigated the primality of the Fermat numbers 2 + 1, and Marin Mersenne studied the Mersenne primes, prime numbers of the form 2 to the power of p1 with p itself a prime. Christian Goldbach formulated Goldbach's conjecture that every even number is the sum of two primes. In a 1742 letter to Euler, Euler proved Al-Hazin's conjecture that all even perfect numbers can be constructed from Mersenne primes. He introduced methods from mathematical analysis to this area in his proofs of the infinitude of the primes and the divergence of the sum of the reciprocals of the primes \frac plus \frac plus \frac plus \frac plus \frac plus dots. At the start of the 19th century, Legendre and Gauss conjectured that as x tends to infinity, the number of primes up to x is asymptotic to x/log x, where \log x is the natural logarithm of x. Ideas of Riemann in his 1859 paper on a zeta function sketched an outline for proving this. Although the closely related Riemann hypothesis remains unproven, Riemann's outline was completed in 1896 by Hadamard and de la Vallée-Buisson, and the result is now known as the prime number theorem. Another important 19th century result was Dirichlet's theorem on arithmetic progressions, that certain arithmetic progressions contain infinitely many primes. Many mathematicians have worked on primality tests for numbers larger than those where trial division is practicably applicable. Methods that are restricted to specific number forms include Pepin's test for Fermat numbers, Proth's theorem, the Lucas-Lemma primality test, and the generalized Lucas primality test. Since 1951, all the largest known primes have been found using these tests on computers. The search for ever larger primes has generated interest outside mathematical circles, through the great internet Mersenne prime search and other distributed computing projects. The idea that prime numbers had few applications outside of pure mathematics was shattered in the 1970s, when public key cryptography and the RSA cryptosystem were invented, using prime numbers as their basis. The increased practical importance of computerized primality testing and factorization led to the development of improved methods capable of handling large numbers of unrestricted form. The mathematical theory of prime numbers also moved forward with the Green-Tau theorem on long arithmetic progressions of prime numbers, and Yatang's 2013 proof that there exist infinitely many prime gaps of bounded size. Primality of 1. Most early Greeks did not even consider 1 to be a number, so they could not consider its primality. A few mathematicians from this time also considered the prime numbers to be a subdivision of the odd numbers, so they also did not consider 2 to be prime. However, Euclid and a majority of the other Greek mathematicians considered 2 as prime. The medieval Islamic mathematicians largely followed the Greeks in viewing 1 as not being a number. By the Middle Ages and Renaissance, mathematicians began treating 1 as a number, and some of them included it as the first prime number. In the mid-18th century, Christian Goldbach listed 1 as prime in his correspondence with Leonhard Euler. However, Euler himself did not consider 1 to be prime. In the 19th century, many mathematicians still considered 1 to be prime, and lists of primes that included 1 continued to be published as recently as 1956. If the definition of a prime number were changed to call 1 a prime, many statements involving prime numbers would need to be reworded in a more awkward way. For example, the fundamental theorem of arithmetic would need to be rephrased in terms of factorizations into primes greater than 1. Because every number would have multiple factorizations with different numbers of copies of 1. Similarly, the sieve of Eratosthenes would not work correctly if it handled 1 as a prime, because it would eliminate all multiples of 1 and output only the single number 1. Some other more technical properties of prime numbers also do not hold for the number 1. For instance, the formulas for Euler's totient function or for the sum of divisors function are different for prime numbers than they are for 1. By the early 20th century, mathematicians began to agree that 1 should not be listed as prime, but rather in its own special category as a unit. Unique factorization. Writing a number as a product of prime numbers is called a prime factorization of the number. For example, begin 34,866 and 2 c.3 c.13 c.149 and 2 c.3 squared c.13 c.149 n. The terms in the product are called prime factors. The same prime factor may occur more than once. This example has 2 copies of the prime factor 3. When a prime occurs multiple times, exponentiation can be used to group together multiple copies of the same prime number. For instance, in the second way of writing the product above, 3 squared denotes the square or second power of 3. The central importance of prime numbers to number theory and mathematics in general stems from the fundamental theorem of arithmetic. This theorem states that every integer larger than 1 can be written as a product of 1 or more primes. More strongly, this product is unique in the sense that any 2 prime factorizations of the same number will have the same numbers of copies of the same primes, although their ordering may differ. So, although there are many different ways of finding a factorization using an integer factorization algorithm, they all must produce the same result. Primes can thus be considered the basic building blocks of the natural numbers. Some proofs of the uniqueness of prime factorizations are based on Euclid's lemma. If p is a prime number and p divides a product ab of integers a and b, then p divides a or p divides b. Conversely, if a number p has the property that when it divides a product it always divides at least one factor of the product, then p must be prime. Infiniteness. There are infinitely many prime numbers. Another way of saying this is that the sequence 2, 3, 5, 7, 11, 13 of prime numbers never ends. This statement is referred to as Euclid's theorem in honor of the ancient Greek mathematician Euclid, since the first known proof for this statement is attributed to him. Many more proofs of the infinitude of primes are known, including an analytical proof by Euler, Goldbach's proof based on Fermat numbers, Furstenberg's proof using general topology, and Kummer's elegant proof. Euclid's proof shows that every finite list of primes is incomplete. The key idea is to multiply together the primes in any given list and add 1. If the list consists of the primes p_1, p_2, dots p_n, this gives the number n1 plus p_1 c.p_2 dots p_n. By the fundamental theorem, n has a prime factorization, np_1 c.p_2 dots p_n with 1 or more prime factors. N is evenly divisible by each of these factors, but n has a remainder of 1 when divided by any of the prime numbers in the given list, so none of the prime factors of n can be in the given list. Because there is no finite list of all the primes, there must be infinitely many primes. The numbers formed by adding 1 to the products of the smallest primes are called Euclid numbers. The first 5 of them are prime, but the 6th, 300,311 plus 2 c.3 c.5 c.7 c.11 c.1359 c.509 is a composite number. Brought to you by WikiVidi Documentaries. Would you like to know more?